Hello friends, welcome to our YouTube channel. We have learned that an electrical network is called a two-port network when it comprises of one input port and one output port. We can describe a two-port network in 6 ways. Each method uses a set of 4 parameters. As all the sets of parameters describe the same two-port network, there exist definite relationships between them. Today, we shall establish interrelationships between T' parameters and the other sets of parameters. Inverse transmission parameters are widely used in the field of power system and telecommunication systems. Let us recall how we have used inverse transmission parameters to describe a two-port network. Inverse transmission parameters are simply called T' parameters. When we describe a two-port network using inverse transmission parameters, we consider the input port variables V1 and I1 as independent variables and output port variables V2 and I2 as dependent variables. The linear equations used in this case are V2 equals to A'(V1) minus B'(I1) and I2 equals to C'(V1) minus D'(I1). These two equations may be written in matrix form as follows. Matrix of V2 I2 equals to matrix of A', B', C', D' into matrix of V1 minus I1. The elements A', B', C', D' are known as inverse transmission parameters or T' parameters. Some of them are measured by open circuit test and some of them are determined by short circuit test. They have mixed type dimensions. These parameters are useful in case of cascaded networks. Let us derive the interrelationships between inverse transmission parameters and Z parameters. When we describe a two-port network using Z parameters, we express the port voltages V1 and V2 in terms of port currents I1 and I2. The linear equations used in this case are V1 equals to Z11I1 plus Z12I2 and V2 equals to Z21I1 plus Z22I2. By rearranging equation number 1, we get I2 equals to 1 upon Z12 times V1 minus Z11 by Z12 times I1. Using this expression from equation number 2, we can write V2 equals to Z21 times I1 plus Z22 into 1 upon Z12 times V1 minus Z11 by Z12 times I1. Rearranging this equation, we can write V2 equals to Z22 by Z12 times V1 minus Z11 Z22 minus Z12 Z21 divided by Z12 times I1. When we describe a two-port network using inverse transmission parameters, the linear equations used are V2 equals to A'(V1) minus B'(I1) and I2 equals to C'(V1) minus D'(I1). Comparing the expressions of V2, we get A' equals to Z22 by Z12 and B' equals to delta Z by Z12, where delta Z equals to Z11, Z22 minus Z12, Z21. Comparing the expressions of I2, we get C' equals to 1 upon Z12 and D' equals to Z11 by Z12. Now we have expressed T' parameters in terms of Z parameters. Now let us establish interrelationships between inverse transmission parameters and Y parameters. When we describe a two-port network using Y parameters, we express the port currents I1 and I2 in terms of port voltages V1 and V2. The linear equations used in this case are I1 equals to Y11 V1 plus Y12 V2 and I2 equals to Y21 V1 plus Y22 V2. By rearranging equation number 1, we can write V2 equals to minus Y11 by Y12 times V1 plus 1 upon Y12 times I1. Using this expression from equation number 2, we can write I2 equals to Y21 V1 plus Y22 into minus Y11 by Y12 times V1 plus 1 upon Y12 times I1. Rearranging this equation, we get I2 equals to minus Y11 Y22 minus Y12 Y21 divided by Y12 times V1 plus Y22 by Y12 times I1. When we describe a two-port network using inverse transmission parameters, the linear equations used are V2 equals to A dash V1 minus B dash I1 and I2 equals to C dash V1 minus D dash I1. Comparing the expressions of V2, we get A dash equals to minus Y11 by Y12 and B dash equals to minus 1 upon Y12. Comparing the expressions of I2, we get C dash equals to minus delta Y by Y12 where delta Y equals to Y11 Y22 minus Y12 Y21 and D dash equals to minus Y22 by Y12. Now we have derived T dash parameters in terms of Y parameters. Now let us establish interrelationships between inverse transmission parameters and transmission parameters, or simply called T parameters. When we describe our two-port network using transmission parameters, we express the input port variables V1 and I1 in terms of output port variables V2 and I2. The linear equations used in this case are V1 equals to AV2 minus BI2 and I1 equals to CV2 minus DI2. Multiplying the second equation with minus 1, we get minus I1 equals to minus CV2 plus DI2. The first and third equation may be written in matrix form as follows. Matrix of V1 minus I1 equals to matrix of A minus B minus C D into matrix of V2 I2, or matrix of V2 I2 equals to inverse matrix of A minus B minus C D into matrix of V1 minus I1, or matrix of V2 I2 equals to 1 upon delta T into matrix of D B C A into matrix of V1 minus I1, where delta T equals to AD minus BC. When we describe a two-port network using T-dash parameters, the linear equations used may be written in matrix form as follows. Matrix of V2 I2 equals to matrix of A dash, B dash, C dash, D dash into matrix of V1 minus I1. Comparing these two sets of equations, we get A dash equals to D by delta T, B dash equals to B by delta T, C dash equals to C by delta T, and D dash equals to A by delta T. Now we have expressed T dash parameters in terms of transmission parameters. Let us now establish interrelationships between T-dash parameters and hybrid parameters. When we describe a two-port network using hybrid parameters, we express the input port voltage V1 and output port current I2 in terms of input port current I1 and output port voltage V2. The linear equations used in this case are V1 equals to H11 I1 plus H12 V2 and I2 equals to H21 I1 plus H22 V2. Now rearranging the equation number 1, we get V2 equals to 1 upon H12 times V1 minus H11 by H12 times I1. Now using this expression from equation number 2, we get I2 equals to H21 I1 plus H22 into 1 upon H12 times V1 minus H11 by H12 times I1. By rearranging, we can write I2 equals to H22 by H12 times V1 minus H11 H22 minus H12 H21 by H12 times I1. When we describe a two-port network using T-dash parameters, we use the following linear equations. V2 equals to A dash V1 minus B dash I1 and I2 equals to C dash V1 minus D dash I1. Comparing the expressions of V2, we get A dash equals to 1 upon H12 and B dash equals to H11 by H12. Comparing the expressions of I2, we get C dash equals to H22 by H12 and D dash equals to delta H by H12, where delta H equals to H11 H22 minus H12 H21. Now we have obtained the expressions of T dash parameters in terms of hybrid parameters. Let us now derive the interrelationships between T dash parameters and inverse hybrid parameters, or simply known as G parameters. When we describe a two-port network using G parameters, we express the input port current I1 and output port voltage V2 in terms of input port voltage V1 and output port current I2. The linear equations used in this case are I1 equals to G11 V1 plus G12 I2 and V2 equals to G21 V1 plus G22 I2. By rearranging the equation number 1, we get I2 equals to minus G11 by G12 times V1 plus 1 upon G12 times I1. Using this expression in equation number 2, we get V2 equals to G21 V1 plus G22 into minus G11 by G12 times V1 plus 1 upon G12 times I1. By rearranging this equation, we can write V2 equals to minus of G11 G22 minus G21 G12 divided by G12 times V1 plus G22 by G12 times I1. When we describe a two-port network using T dash parameters, the linear equations used are V2 equals to A dash V1 minus B dash I1 and I2 equals to C dash V1 minus D dash I1. Comparing the expressions of V2, we get A dash equals to minus of delta G by G12, where delta G equals to G11 G22 minus G21 G12, and B dash equals to minus of G22 by G12. Now let us compare the expressions of I2. Now we can write C dash equals to minus G11 by G12 and D dash equals to minus 1 upon G12. Now we have obtained the expressions for T dash parameters in terms of inverse hybrid parameters. Let us solve a couple of numerical problems to implement the interrelationships we have developed so far. The Z parameters for a two-port network are given as Z11 equals to 10 by 3 ohm, Z12 equals to 2 by 3 ohm, Z21 equals to 2 by 3 ohm, and Z22 equals to 4 by 3 ohm. We have to determine inverse transmission parameters using interrelationships. We know for Z parameters, delta Z equals to Z11 Z22 minus Z12 Z21. Putting the values, we get 10 by 3 into 4 by 3 minus 2 by 3 into 2 by 3 equals to 4. Now using interrelationships, we know A dash equals to Z22 by Z12, that is equal to 4 by 3 divided by 2 by 3 equals to 2. B dash equals to delta Z by Z12, that is equal to 4 divided by 2 by 3 equals to 3 by 2 ohm. C dash equals to 1 upon Z12, that is equal to 3 by 2 mho, and D dash equals to Z11 by Z12, that is equal to 10 by 3 divided by 2 by 3 equals to 5. In this problem, transmission parameters for a two-port network are given as A equals to 2.5, B equals to 13 ohm, C equals to 0.5 mho and D equals to 3. We have to determine inverse transmission parameters using interrelationships. We know for transmission parameters delta T equals to AD minus PC. Putting the values we get 2.5 into 3 minus 13 into 0.5, that is equal to 1. Let us use interrelationships to derive inverse transmission parameters. A dash equals to D by delta T, that is equal to 3 divided by 1 equals to 3. B dash equals to B by delta T, that is equal to 13 divided by 1, that is equal to 13 ohm. C dash equals to C by delta T, that is equal to 0.5 divided by 1, that is equal to 0.5 mho. And D dash equals to A by delta T, that is equal to 2.5 divided by 1, that is equal to 2.5. So today we have established relationships between inverse transmission parameters and the other sets of parameters. With the help of these interrelationships, we can easily find inverse transmission parameters when we have another set of parameters readily available. Finally, we have solved a couple of numerical problems to have hands-on practice on implementation of these interrelationships. So that's all I have for you today. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.